Okay. So last lecture we have discussed about the uh, ingot casting, and in this lecture we will discuss about the continuous casting. And the major thing that I would like to cover are the advantage of continuous casting first, and then various units of continuous casting, and also various units as well as functions of different continuous casting units and defects in the continuous casting. So, continuous casting advantage, what are the advantages? If you say first is the yield is much higher compared to the ingot casting. Okay, because in this case you do not form any the pipe because you are continuously feeding it, because casting is made continuous mode and your feeding is continuous. So, piping loss is not there, that is why yield is higher obviously, and productivity is very high because it is a much faster process, very fast solidification process, and it is a continuous process. So, it is not a batch process, that is why the productivity is much higher, because in batch process you feed it, there is a gap, here you are continuously feeding, and also the solidification rate is much faster. So, productivity is high. The structure, finer structure, there is the fast cooling rate. So, because of fast cooling rate your structure obviously will be finer. Energy saving, this is the very important thing of the continuous casting, you basically integrate different processes. In case of the ingot casting, what you do, first you cast the ingot and then take out the ingot at the room temperature, and then again you heat the ingot from the room temperature to a very high temperature above the recrystallization temperature, and then you roll it to produce the more sellable products like sheets, wire, rods, like this. So this process in continuous casting all are integrated. Here the casting need not to be cooled to the room temperature. When you cast it and then it can be reheated, it is also goes to the reheating furnace, but its temperature is quite high, surface temperature 700, 800 to again you have to take it to little higher temperature for to go above the recrystallization temperature for hot rolling. So here, so directly you cast it and then directly it goes to the reheating furnace for incremental increase in temperature, and then directly it goes to the your hot strip mill. So that is why there is a lot of energy saving compared to the ingot casting because of integration of different processes. And then segregation is less because the faster solidification, as I said, if the solidification rate is much faster, because solid do not get sufficient time to get rejected. So segregation will not be that high. But the impurities also, that is why in the, and also another problem is that in case of the faster solidification, your impurity tolerance also become very low, because if the impurity forms also inclusion as well as also the gaseous product, then they do not get sufficient time to come out of the casting. As a result, blowholes forms. That is why in continuous casting obviously we have a very low impurity tolerance. So, we first make the steel with a very low impurity, both solid impurity as well as the gaseous impurities. That has to be much as low as possible, and then we cast it. And finally, your segregation becomes less because of faster solidification also. What is the disadvantage? Disadvantage is subjected to stresses in continuous casting, as we will say, to guide the casting in a particular path. Continuously it is under stress, the roll pressure is there on the surface, okay, pulling through the rolls, and which is aggravated in presence of the thermal strain that generated. Obviously, it is a fast casting process, the thermal strain generated is much higher. So, thermal strain is there as well as roll pressure is there, that basically subjected to stresses, right. So, subjected to stresses due to continuous pulling through the rolls, which is aggravated in presence of thermal strain as well as phase transformation to everything. So, as a result, they can form some point of weakness and the crack formation. I will come to that thing. Now, features and various units of continuous casting. As you see, it is the continuous casting setup. You know, this is the teaming ladle. From teaming ladle, liquid steel is poured into the turn dish through argon shrouding. There is the liquid steel is coming to the turn dish. From turn dish, now from here there is a continuous casting sum. Then the liquid is poured into the mold. This is the mold you can find. This is called the copper cooled, the water cooled copper mold is there, where you pour the liquid steel. and this liquid steel is poured through an enclosure that is called the submerged entry nozzle. So, the liquid is completely enclosed from the atmosphere, it does not have any interaction with the atmosphere. So, it is a nozzle through which the liquid comes and injected inside the liquid. So, the liquid is injected not at the top surface, just inside the below the meniscus, the liquid is given there. Okay, so that is basically, if I just draw it, it will look like this. If you have a copper cooled mold like this, and this will be your seine, and the liquid basically come out, there is a hole come out like this. This is the liquid steel meniscus. Okay, so the liquid is coming through it here. Here is your liquid. This is the enclosure completely. So liquid steel are coming through this seine. This is, if you can call it seine, submerged entry nozzle, and the liquid steel is coming through it. This is the liquid steel, say the liquid steel come and then coming out like this. Okay, so this is called seine, that is the submerged entry nozzle. I will talk about that thing, such that there is no interaction, because when you are putting the liquid steel into the mold, now we cannot allow any further interaction with the atmosphere. Then inclusion cannot be removed, because the last resort Tandis we have removed all the inclusions. So I don't want to include the inclusions here, because as you more interaction with the atmosphere, it will absorb oxygen and the nitrogen that have to be avoided at the final stage. So that's why you use a submerged entry nozzle. There's the shrouding is also not good here. A completely liquid will come completely through an enclosed pipe. Okay, so the liquid is coming through this pipe without any interaction and then emitting into the inside the liquid steel. You can see the liquid is coming out below the meniscus. Okay, so there is no absolutely, and here basically mold powder is there. So there is no interaction with the atmosphere. Liquid steel don't have any interaction with the atmosphere. So seine basically helps. And then comes the water cooled copper mold. That is, the copper mold is usually cooled with the water. Copper is a very high conductivity, so it heat extraction rate is very high, and also the liquid water is also there. So heat extraction, because why the heat extraction rate has to be high, because when the liquid steel is coming out, this will form some skin. So you can find that it will come like this. So inside it is liquid. So this is called the skin thickness. So this thickness, solidified shell thickness, should be sufficient here. Otherwise, such that the inside you can see there is a liquid. When the casting is coming out, the core of the casting, there is totally liquid and lot of pressure is there. So this liquid pressure can break the casting and can come out if the skin thickness is not sufficient. So you have to develop a sufficient skin thickness such that the internal pressure of the liquid cannot break it and come out. So that's why you require and the mold thickness also, mold length is also not high. It may be maximum of the order of 1 meter. So okay, so mold distance, that is the length of the mold, is not very great. So what you have to do, basically you have to extract the heat at a very faster rate. So that's why it is used basically the copper mold. Very high conductivity, it can easily extract the heat. And also it is water cooled such that it increases the heat extraction rate. Okay, so that's why you use a water cooled copper mold such that you can develop a sufficient thickness, exit thickness, when the casting is coming out from the mold. And then what happens when you are coming out, that is when we are coming out from the mold, you can find this is called the secondary cooling. Here a lot of spray systems are there. Here basically you have lot of spray are there, water spray systems are there. It is you can find the roll basically guiding the casting, and you have a lot of spray system is there. Through the water jet goes and it cools the surface, because you can see here it is liquid. Still here the core there is liquid and the liquid is completing here. So here you can find it is completely solidified at this range, but before this your core was liquid. You had only skin thickness, and skin thickness increases with time in the secondary cooling zone also, and finally you get completely solidified casting. Okay, so it goes on. Then That is the use of that is the water cooled copper mold I talked about. Then the mold powder. Mold powder is also very important because mold powder are very fluid slag, basically you can say, that has some purpose. One purpose is that to avoid the interaction, atmospheric interaction, as well as it lubricates the mold surface. It lubricates the mold surface. As a result, you can take out the casting very fast. It also increases the heat transfer rate also. I will come to that thing. So mold powder has a great role to play to enhance the heat transfer and then to easy removal of the casting. Otherwise, what happens? The liquid still, if they are welded with the mold wall, you cannot cast it continuously. Okay. So the casting surface has to be totally lubricated such that you can take out the casting. And then you have EMS, electromagnetic stirring. You have electromagnetic stirring in the mold, that is the liquid gets stirred, and that has very beneficial effect. I will come to that. That is the central line segregation you can avoid out of it. And then also you can increase the heat transfer like that. EMBR, electromagnetic break, is here. Here with the liquid, when the liquid is coming out from the seine, it is coming out is a high speed jet. So you have to break the turbulence. Otherwise, it can incorporate the mold flux into the casting structure and produce a lot of inclusion defect. That is the exogenous inclusion defects. Okay. And then mold oscillation. This is very important. The mold is also, it is not stationary. Mold is also oscillating in a sinusoidal mode like this. As a result, it also helps in such that the casting do not get welded with the surface. So it always oscillates. And the secondary cooling, as I said, secondary cooling is required because the internal, that is the internal core is the liquid, so that has to be solidified. So you have to extract the heat, even if it coming out of the mold, then you have to extract a lot of heat such that the complete cross section gets solidified. Okay. So that's why secondary cooling is important. Secondary cooling is nothing. After this coming out of the mold, you have a lot of water spray supply, water jet supply is there, and that basically cools from the surface. So heat comes from the center to the surface and go away. So first is the seine, as I said, mold units and their function. That is the seine, the submerged entry nozzle, as I said, to reduce the oxidation and nitrogen pickup. That is the reduce the atmospheric interaction. That is the second is the AMBR, that is the electromagnetic break. As I said, when the liquid is coming out of the seine, they come out at a high speed liquid jet that interacts with the mold wall very strongly. As a result, the lubricant can be entrained into the liquid metal and come into the structure. And finally, they can solidify and a lot of inclusion it will give. So this is not a good thing. And also a lot of turbulence take place. And this turbulence also can increase the inclusions. That is the main thing also, that it can break the mold flux at the top, and from the top also you can have a lot of atmospheric interaction. So high speed liquid jet emitting from the seine passes through a magnetic field to dampen basically the turbulence, reduce the mold powder entrapment, that I said. If you see in this case, there is from the seine, there is the liquid is coming through a jet, and very high speed jet, it is moving like this. And you can see a lot of mold powders are getting entrapped into the liquid still, and when they solidified, they will be there as an inclusion. So what you do, basically you break the turbulence by applying an electromagnetic force here. So that is called the electromagnetic break. You can damp the turbulence and the liquid moves smoothly like this in a plug flow pattern. Okay. So that's why. That is, reduces the mold powder entrapment, reduces the chance of crack formation and the breakout. It can also increases the chance of breakout. Breakout means if the solidified skin at the exit of the mold suddenly break. So if you have a lot of turbulence, that can melt the exit skin from the mold. Okay, the casting skin, that is when the casting is coming out, the skin can be break because of very high turbulence, and then it is also called the bleeding and breakout. Okay. So then water cooled copper mold, as I said, faster heat extraction, and also one thing you can see, this mold is not it is not perfectly cylindrical. It is little tapered in, actually tapered from the top to the bottom to account for the solidification shrinkage. That means it is tapered like this. Mold is not exactly mold is not exactly cylindrical, it is slightly tapered like this, it is not too much tapered, it is slightly tapered. So if I draw it like this properly, right. So this much tapering is there, you can find slight tapering is there. Why this tapering? Because if you use this tapering, and then this type of tapering is essential, because as the liquid metal is coming down, right, as the liquid metal is coming down here, the solidification is taking place. As the solidification is taking place, it will string. So you have to reduce the volume. Otherwise, what will happen? There is the air gap entrapment, there is a gas entrapment will be there. That is because of shrinkage, void will be forming, and that voids can decrease the heat transfer through the mold wall. So this much of tapering is there. And the mold powder, what are the function of the mold powder? It has main function is the lubrication. At the wall, it gives the lubrication, and then enhance the heat transfer by penetrating gas at the mold surface, because the mold powder, as I said, they should be very fluid also. They should have low liquidity and fluid, such that if some gas pockets are formed at the mold solidified shell interface, they can penetrate those gas, and then, because if they can penetrate, then the conductivity will increase, because this mold powder, this is a mold flux, those are very highly conducting. So if they can penetrate the gas, basically any entrapped gas at the solidified shell mold interface will increase the heat transfer resistance, because gas is not conducting. So if your that is the mold powder is very fluid, they can easily penetrate the gas pockets, and then they can increase the heat transfer coefficient at the mold solidified shell interface. It is very important, because the heat flux, you have to extract the heat at a very faster rate, as I said, because mold length maximum may be 1 meter, and you have to extract the heat in sufficiently such that when the casting is coming out, you have a sufficient skin thickness. Okay, so that is the thing. And also mold powder basically is enhance the heat transfer by penetrating gas at the mold surface, and it is made of SiO2, CO, Al2O3, Na2O, because Na2O, CF2, you can understand they are giving for, they are very highly conducting in addition to this thing. So this is the typical composition of the mold powder. So then we are coming to the electromagnetic stirring, and the mold has some electromagnetic stirring, because the liquid has to be stirred somehow. Otherwise, if you don't have electromagnetic stirring, there would be only in the liquid still will be in motion only because of natural convection. That is a very mild convection. That convection is not sufficient sometimes, because if you have electromagnetic stirring, you can have a sufficient stirring inside the bath. It promotes the equiaxed grains at the center and removes the central line segregation. How it is possible? How it promotes the equiaxed grains at the center? Because as I said, first during the solidification at the surface, you have a skin thickness. After that, columnar grain grows. So columnar grain basically in the mold, if you see the columnar grains, it will grow like this. From the surface, it will grow like this and like this. And it will push the impure liquid. It will basically push the impure liquid just at the center of the casting. So impure liquid will be pushed at the center of the casting. When they get solidified, here there will be huge positive segregation across the central line, and that is called the central line segregation. And the solidification structure is like this. So columnar grain process like this. So if you have a stirring here, then what will happen? The stirring will cross, that is the break this dendritic tips. Because of stirring, this dendritic strips will be broken, and then these dendritic tips will act as an heterogeneous nucleation site. So you can develop the equiax structure, equiax dendritic structure in near the center. Okay. So as a result, this macro segregation will convert to a micro segregation, interdendritic segregation, because the center will be now equiax dendritic, and the segregation will convert to a micro segregation, interdendritic segregation, not a macro segregation just like this. Here what was happening, the liquid is pushed by the columnar grain, and final liquid is very rich in impurity. So central line segregation will be there, and it is very prominent. So if you use the EMS, it will break the dendritic tips. Those tips will act as an heterogeneous nucleation site. So a large central region will be there which will be equiax dendritic. So that morphology will promote the micro segregation, interdendritic segregation rather than a macro segregation. As I said, the central line segregation is the macro segregation is a defect, but interdendritic segregation is not a defect. If you annihilate, you can simply annihilate the segregation. How? Because from the interdendritic region, if you heat it, interdendritic region, the impurity or there is a solute will move to the dendrites, and they are very nearby. So they can easily move to the dendrites, and then uniform of composition will take place between the interdendritic region and the dendrite. So that way you can micro segregation you can eliminate. So that is the thing. By EMS basically promotes the equiax grain, and that basically reduces the central line segregation. And also the EMS will also reduce the slag entrapment. How the slag entrapment? Because if some mold flux, obviously some mold flux will be entrapped into the structure, whatever the you are using EMBR, so propensity will be much less, but some mold flux will be there inside the liquid. And if you have a stirring, then those inclusions will move with the liquid still, and they will reach the top surface, right? They will move, like the circulation loop will be there. So as a result, that is this inclusion inside, this inclusion from inside can move towards the top slag or the top mold flux and can be engulfed there, and they can be engulfed into it. So this mold flux will be collected at the top surface, so they will be coming. So basically the stirring can help to carry this mold flux to the top surface and deposit it there. That's why it reduces the slag entrapment also, and reduces the pinhole on the surface. And it can reduce the pinhole on the surface, that is all because if you have a stirring action over the wall, so your heat transfer will be more uniform. Okay, so if heat transfer is uniform, that is because basically pinholes on the surface of the mold take place because of non-uniform heating on the surface, non-uniform heating, because some region there may be very high resistance, some region less resistance, because mold flux is not uniformly distributed across the surface. So as a result, some region will be very high conductance, some region will be less conductance. So some hotspot generate the regions where heat transfer resistance is more. As a result, those are the weak points, and then there are some pinholes or types of defects can take place. So if you have a stirring, basically you are homogenization, that is that in the liquid temperature is very uniform every time, and as a result, and also because of stirring, that is the mold flux distribution on the surface will also be much more uniform. Okay, so those are the things. Now it is a very important thing is the mold oscillation. This basically facilitates the easy extraction of the casting from the mold. Basically mold oscillates in a sinusoidal mode. You can see that is the mold velocity versus the time. This is the time, and you can see initially the mold moves in the similar direction that of the casting, that is the mold is moving down. Casting is always moving down, so mold is moving down, and then it is increasing its velocity, and then it decreases again, becomes 0, and then again it moves in the opposite direction. There is opposite to that, there is move in the upper direction, and mold is always moving, casting is moving always in the bottom direction, and now the mold is moving in the upper direction, so opposite direction. So this way it can go. Now you can find when the mold is moving in the towards the bottom, that is when it is coming out, that is when the mold is moving the similar direction to that of the casting. There exists some time, during this time from here to here you can find the velocity of the mold is greater than that of the casting. This is the casting velocity, this is the casting velocity, and in all this region you can see the velocity of the casting is greater than that of the mold, greater than that of the casting. The velocity of the mold is greater than that of the casting in this region. Okay, so this is called the negative stripping. This is called the negative stripping. There is during the downward movement of the mold, there exists a period when the mold moves with a speed greater than that of casting, and this is called the negative strip time. And this basically, there is the mold is moving is much faster compared to the casting. So as a result, this basically helps in releasing the casting from the mold. Okay, so mold moves much faster compared to that casting. So this allows the release of the shell from the, and this time is called the negative stripping. This time range is called the negative stripping. And there is also another time is called the positive stripping, when the basically when the mold moves in the opposite direction and its velocity, mold velocity is greater than that of the casting, then it is called the positive stripping, this region time. So it basically what happens, this positive stripping time, it deposits the mold flux on the solidified shell wall and lubricate. So during the positive stripping, basically you lubricate the surface. During negative stripping, you basically facilitate the release of the casting. So this sinusoidal mode of movement of the mold is very much helpful. Now I come to the defects in the casting. Okay, some defects. Now there are several defects that take place, and why this defect take place in the casting, as I said at the beginning, because the casting is subjected to lot of stresses. Thermal stress is there, and then mechanical stress because of the roll, guiding roll, pinching roll, all these things. Okay, and some phase transformation associated with some phase transformation. For example, a low carbon steel, if you cast it, then there is the delta to gamma transition. That is the phase transformation is there, and then there can be some pinhole, that is in the casting structure, which can propagate into the cracks later on, or the point of weakness may be there on the structure in the mold. And then you can have, depending on the impurities, lot of precipitation take place during the casting. Okay, and this precipitation can take place, all this type of precipitates, harsh precipitates, are the point of stress concentration. So if we apply the stress, that also that can generate lot of cracks. Okay, so there are different internal cracks. You can find these internal cracks are these are inside the cracks, inside the structure, that are called the internal cracks. They are basically generated because of this different type of stress, non-uniform stress distribution across the whole size of the billet and casting, the slabs, billets, and all these things. So you have non-uniform stress distribution because the surface, some surface is much wider compared to the thickness. As a result, heat transfer is different in different direction. So heat transfer rate is different. As a result, thermal stress is very non-uniform. So those basically gives rise to lot of internal cracks. There are some cracks which are on the surface. There is the longitudinal surface cracks and the transverse surface crack. And these cracks also penetrate to some extent deep inside the casting also. And internal cracks are not you cannot consider as a defect, because when you just roll it, they will be rolled together and they will never be exposed to the atmosphere. So internal cracks will be rolled and never exposed to the atmosphere. So those defects are not that dangerous. So okay, you may not call them as a defect, internal cracks. Okay. But on the other hand, the most defects are basically the surface cracks are the defects, because surface cracks are exposed to the atmosphere and they get oxidized. So unless you peel off the completely, and whatever the depth, depending on the depth of those surface cracks, you have to peel off the surface. So those are basically the defects. Surface cracks are very dangerous. So we'll discuss basically more on the surface cracks. Okay, and also one more important defect in the casting is the central line segregation. Okay, so that is one of the another important defects. Another defects is the blowholes and then inclusions. Those are some of the defects. So we'll just talk about what are the corrective action to eliminate these defects. So major defects and the remedial measures. Let us first consider the central line segregation. What are the causes? There is the extension of the columnar zone up to the central line. As I said, when they extend, they pushes the impure liquid near the center, and finally when they solidify, the center become impurity rich, and that is called segregation, positive, huge positive macro segregation. What are the influencing factor? It is as I said, the high superheat basically will promote, and low casting speed. Why? You can simply see G by R. What is the G by R? G by R, if you high superheat means gradient is very high, low casting phase R is less. So G by R is very high. So if your G by R is high, then columnar grain is will be more prominent. Okay, there is be more there's the morphology will be the columnar grains, and columnar grains basically increase the propensity of the central line segregation. So that's why these are the influencing factor. And what are the corrective measures? Just opposite, you should have a low superheat and you should have high casting speed such that G by R become less. If G by R is less, then you can promote the equiax dendritic structure at the center. So your central line macro segregation will be converted to the micro interdendritic segregation. Okay, that can be easily eliminated during the annealing. Okay, so that's why this thing, low pouring temperature, high casting speed is there. And besides EMS, obviously EMS plays a very important role. If you have an EMS, it will break the dendritic trips. That is the columnar grain trips. It will break the columnar grain trips, and this columnar grain trips then act as a nucleation site, heterogeneous nucleation site for the finer, that is for generating a very equiaxed dendritic structure near the central region, and that's why the EMS can help. Next inclusion, there is the inclusion and blowholes are also the defects. So entrapment of the solid inclusions and bubbles during the continuous casting. So we should be very cautious as that there is no atmospheric interaction. That's why we have used SEN. Okay, and also we have also used the electromagnetic brake to avoid the mold flux inclusion into the casting also. Okay, so those you have to, these are the causes basically. And influencing factor is the gas absorption during teaming, and not only that during teaming, so that we have to take care of. And that's why during teaming, from liquid steel from the ladle to the tandis, it is some gas surrounding, argon gas surrounding is used. But nowadays, replacing the gas surrounding, people are using a continuous nozzle just like SEN. Okay, people are using the SEN such that it do not have, it just eliminate the 100% any atmospheric interaction, even in the tandis to the even from the teaming ladle to the tandis. Obviously, tandis to mold we have the SEN, but we can use the similar setup in teaming ladle to the tandis also, such that you can eliminate any 0% of atmospheric interaction. You can make the atmospheric interaction to 0%. Okay. So anyway, the influencing factor is there, gas absorption during teaming, and impurities in the steel. So you have to look into your impurity into the steel. The secondary processing should be sufficient such that no impurities exist. And also that's why in the tandis we have also some option for tandis now. You have to design the tandis in such a way such that you can promote the plug flow and you can remove the inclusion. Even in the continuous cast mold also, we have EMS, electromagnetic stirring, such that we can facilitate the float up of the inclusion to the surface of the mold flux, such that the mold flux from the liquid steel can be deposited at the top surface, okay, top mold flux in the meniscus region. Okay, so those are the things. And then what are the corrective action? You can use the SEN and EMBR. SEN obviously is there, so low zero interaction, and EMBR, electromagnetic brakes, such that the mold flux incorporation will be less, and the proper ladle and tandis treatment, that is the thing. Okay. And now I am coming to the surface defects. Those are the very important. One is called the transverse surface defects and the longitudinal surface defects. And transverse surface defects, they basically occur, it has been found that straightening through an unfavorable temperature region, that is a 700 to 900 degrees centigrade. If you straighten it, then what happens, it has been found that is on the transverse cracks, lot of nitrites precipitates are there. And nitrites precipitation take place in the temperature range of 700 to 900 degrees centigrade, especially if the structure is strained. Okay, so that's why the straightening through an unfavorable temperature region that deposit lot of nitrate precipitates into the transverse cracks. Basically, this precipitate acts as a stress concentrator, and if some weakness is there, and then they basically propagate in the form of transverse crack. Strongly influenced by the composition like aluminum, vanadium, niobium, manganese, those are the strong nitrate formers. If you have, then basically they leads to this thing. maintain the surface temperature above 900, there is the corrective action during straightening. When you straighten it, you do it at higher temperature where the nitrogen precipitate is not that very strong, and reduce the nitrogen in the liquid steel by upstream processing, vacuum, all these things. Now another thing is the longitudinal cracks. Longitudinal cracks, this is basically strain generated in the mold and the upper spray zone. It is telling the strain that is generated, that is basically cause of the longitudinal cracks, and it is aided by something. There is a phase transformation like low carbon steel. It has been found longitudinal cracks are very more more likely into the low carbon steel, because in low carbon steel a phase transformation delta to gamma transformation give rise to some kind of shrinkage, and overcooling in the upper spray zone, that is also a problem. If you do the overcooling, that is the stress generation will be more, and this is another factor. There is a lower Mn to S ratio, or the sulfur is high compared to the manganese. Okay, so lower Mn/S ratio or high sulfur, because if sulfur is very high, this it has been found it is the propensity for the longitudinal cracks is more. And wicks, basically possibly the sulfur can form the iron sulfide if manganese is less, and then iron sulfide is low melting eutectic, so it can make the point of weakness for the and the stress can propagate the crack. Weak spot generated in the mold, all these things. Weak spot generated, there is a pinhole or the hot, that is a hot spot that is generated on the mold wall also, that generates this thing. What are the corrective action? There is the more uniform cooling in the mold, and the more there is a reduce the cooling in the upper spray zone. Upper spray zone, if you are very fast cooling, you don't do that, because strain generation become very high, because interior is the liquid and the surface become very surface. If you have a very there is the upper spray region, if you just cool it very faster rate in the secondary cooling zone, upper of the cooling zone, then the surface will get very cooled, but the center remain very hot. So that gives rise to a reheating, because when the heat from the center come to the surface, it gets start reheating. So that gives rise to reheating. That is the, so that basically cycle of heating reheating, that gives a lot of strain generation. And also the lower casting rates and the low superheat obviously will be very good. Lower casting rates, so if your casting rate is low, you allow sufficient time for the heat from the center to go out, and the low, because it is basically if your cast is at a very fast rate, then you do not have sufficient time to take out the heat from the core of the casting towards the surface. So that is the thing, then that results the reheating of the surface. And low superheat, if you have a low superheat, then the heat extraction rate also can be reduced. If you have very high superheat, lot of heat has to be extracted, that's the load become more, and the thermal strain generation also become more. So obviously, so with this I will conclude, and this is all self-explanatory. Okay. So, and the products, what are the continuous casting products? Basically the slab, billets, and the bloom. Slabs are rectangular size, and the biggest, that is typically 800 to 1300 millimeter wide, and its thickness is 150 to 300 millimeter. And billets are cast in a square cross section 150 by 150, and blooms are bigger than billets. They can be both square as well as rectangular, but little bigger than that of the billets. Okay, and the biggest breakthrough of continuous casting in recent times is the thin slab casting. They can cast 50 to 80 millimeter thickness. Okay, I'll talk about in the next lecture. And the strip casting, and that can directly cast 1 to 5 millimeter thickness. Okay. So these are the conclusions, and thank you very much.